In the darkness of space, a tiny overlooked planet dances dangerously close to the sun. It's often forgotten. It has no rings, no moons, and little in the way of spectacle. But what lies beneath its plain grey surface is astonishing. A giant iron core. Temperatures more extreme than anywhere else in the solar system. Ice locked in perpetual shadow. And a surface so ancient it holds clues to the very beginnings of our solar system. This is Mercury, the smallest planet, the closest to the Sun, the fastest to orbit, and one of the most misunderstood. Scientists once thought it was geologically dead, lifeless, airless, simple. But Mercury has proven to be anything but simple. It defies expectations, a planet of contradictions. It is simultaneously burning hot and freezing cold. It has an atmosphere so thin it's nearly a vacuum, and yet a magnetic field like Earth. Its rotation and orbit create a solar day longer than its year. Its core dominates its interior, suggesting it once may have been something very different. This documentary will explore every aspect of Mercury's scientific, from its wild temperature swings and alien geology to the spacecraft that have dared to visit. We'll dive into its mythology, examine its strange composition and reveal the many questions that still surround it, because Mercury is more than a grey ball of rock. It is a survivor, a cosmic relic, and maybe the key to understanding how rocky planets live and die. Let's begin with the basics. Mercury is the first planet from the Sun, orbiting at a distance of about 58 million kilometers, or roughly 36 million miles. That's just 0.39 astronomical units, less than half the distance between Earth and the Sun. In terms of size, Mercury is the smallest planet in the solar system. It's just 4,880 kilometers, or 3,032 miles across. That's smaller than Jupiter's moon Ganymede. It's only slightly larger than Earth's moon, yet it's more massive than the moon, nearly 5.5% the mass of Earth, thanks to its incredibly dense interior. In fact, Mercury is the second densest planet in the solar system, right after Earth. Why? Because its core is enormous. We'll get into the core soon. But for now, let's talk about how Mercury moves. Mercury orbits the Sun once every 88 Earth days. That means a year on Mercury is just under 3 Earth months. But here's where it gets strange. Mercury rotates on its axis once every 59 Earth days, and because of how its rotation and orbit interact, a single solar day, from one sunrise to the next, lasts 176 Earth days. So a day on Mercury is twice as long as its year. And it's not just the timing that's weird. If you stood on the surface, you'd see the Sun rise slowly, stop, reverse slightly, and then continue its arc across the sky. This phenomenon, caused by Mercury's orbital eccentricity and rotational resonance, means its sunrises are some of the strangest in the solar system. Speaking of orbits, Mercury's is not a perfect circle. It's highly elliptical, meaning it varies significantly in distance from the Sun, more than any other planet. At its closest, called perihelion, Mercury is about 46 million kilometers from the Sun. At its farthest, aphelion, it's about 70 million kilometers away. This eccentric orbit causes Mercury's speed to change drastically as it swings around the Sun, moving faster near perihelion and slower near aphelion. And that's why Mercury got its name. To ancient Romans, this fast-moving star in the sky was associated with Mercury, the fleet-footed messenger of the gods. Mercury is a planet of extremes, unlike any other in the solar system. Let's start with its most notorious feature, temperature. On the day side, Mercury bakes under the raw, unfiltered heat of the Sun. Temperatures can reach a searing 430 degrees Celsius. That's 800 degrees Fahrenheit, hot enough to melt lead. Yet only a few hundred kilometers away, on the night side, the surface plunges to a bone-chilling minus 180 degrees Celsius, or minus 290 degrees Fahrenheit. This means Mercury experiences the greatest temperature swing of any planet in the solar system, over 600 degrees Celsius from day to night. Why? Because Mercury has virtually no atmosphere. Unlike Earth, which has a thick envelope of gases to trap heat and regulate climate, Mercury's atmosphere is so thin it's essentially non-existent. It does have an exosphere, a fragile shell of atoms that are blasted off the surface by solar wind and micrometeoroid impacts. But this exosphere is far too thin to carry sound, weather, or even proper air pressure. It contains trace amounts of sodium, potassium, hydrogen, helium, and oxygen, but not enough to do anything like trap heat or create clouds. In fact, standing on Mercury, you would see the sun rise and set in a black sky. There would be no blue sky, no winds, no breathable air. The silence would be total, not just because there's no life, but because there's no medium to carry sound. Imagine you're in a crater on Mercury's equator. The horizon is a soft arc, the ground covered in fine grey dust and jagged rock. There's no air, the temperature beneath your boots is rising fast. You look up and you see the sun, not yellow-white like on Earth, but a blinding ball of light nearly twice the size it appears from Earth. It creeps upward in a strange, stuttering arc, pauses, seems to reverse, and then resumes its rise. That's no trick of the eye. It's Mercury's odd 3-to-2 spin-orbit resonance in action. The result? A single sunrise can last for hours, and sometimes the sun appears to rise, set, and rise again, all in the same Mercurian day. Now imagine that same landscape just a few hundred kilometers away on the night side. The temperature is so cold it's comparable to the farthest dwarf planets in the solar system. No atmosphere means no insulation, no heat redistribution. It's a world of scorching daylight and frozen darkness existing side by side. Now, add one more twist. Because of Mercury's elliptical orbit, the intensity of sunlight changes over time. When it's closest to the Sun, at perihelion, sunlight is not only brighter, but Mercury also speeds up in its orbit, stretching its already strange day-night cycle. Even Mercury's poles, which receive much less sunlight than the equator, are home to deep craters that are permanently shadowed. And inside those cold traps, scientists have found water ice, a shocking discovery on a planet so close to the Sun. The idea that frozen water could exist on Mercury was once considered impossible, but thanks to radar observations and MESSENGER's data, we now know it's real. That's Mercury in a nutshell, impossible on the surface, but full of surprises. Mercury's surface is a geological time capsule, a preserved relic from the early solar system. Because it lacks wind, water, and plate tectonics, Mercury's landscape has barely changed in billions of years. It's pockmarked with impact craters from ancient collisions, many of them unchanged since the late heavy bombardment over 3.8 billion years ago. Craters range in size from a few meters across to the massive, multi-ringed Caloris Basin, one of the largest impact structures in the entire solar system. The Caloris Basin is enormous, over 1,500 kilometers wide. That's nearly the width of Western Europe. It was formed by a titanic impact, likely from an asteroid 100 kilometers across, slamming into Mercury at incredible speed. The collision not only created the basin itself, but also generated shockwaves that rippled through the entire planet. On the exact opposite side of Mercury, those waves converged and shattered the surface, creating a bizarre region known as weird terrain. This chaotic region is made up of jumbled ridges, grooves, and distorted ground, the planetary equivalent of a bell ringing from the inside. And this isn't an isolated feature. Craters like Tolstoy, Rembrandt, and Shakespeare also showcase multi-ringed structures and volcanic infill. Yes, volcanism. Mercury wasn't just hit from above, it once erupted from below. MESSENGER's data confirmed that large swathes of Mercury's surface were shaped by ancient volcanic flows, some stretching hundreds of kilometers. Much of this resurfacing happened in Mercury's early history, but some features suggest volcanism lasted longer than previously believed. One of Mercury's most fascinating geological signatures are its enormous lobate scarps, giant cliffs created by planetary contraction. As Mercury's core cooled over time, the entire planet shrank by up to 7 kilometers in radius. The crust, unable to compress smoothly, cracked and folded, forming long, steep cliffs. Some are over 1,000 kilometers long and up to 3 kilometers high. These cliffs are visible across the surface, some cutting directly through older craters, which tells us they formed later. In fact, some scarps show no signs of erosion at all, leading scientists to believe that Mercury may still be geologically active, slowly shrinking even today. Another mystery hollows. These are strange, shallow, irregular depressions found in crater walls and floors. They appear bright, reflective, and often cluster in groups. They don't match any known volcanic or impact processes on other planets. Scientists believe they may form when volatile elements, like sulfur or potassium, sublimate directly into space, leaving behind voids. What's more, hollows seem to be geologically young, possibly still forming today. No other planet in the solar system has them. They are uniquely Mercurian. In visible light, Mercury appears grey, almost colourless. But when enhanced with colour filters, its surface reveals subtle shades of red, blue and orange, showing different mineral compositions. Areas with higher iron content appear bluer. Ancient plains and volcanic flows show reddish or tan hues. These variations offer insight into the planet's internal chemistry and hint that it formed in a very different environment than Earth or Mars. Mercury's surface may look dead, but it's speaking to us. Through craters, cliffs, volcanic plains and bright hollows, it tells the story of violence, heat and evolution. Of all Mercury's strange characteristics, none is more surprising or important than its core. Mercury's iron core is enormous. It makes up about 85% of the planet's radius, by far the largest core-to-body ratio in the solar system. Compare that to Earth, where the core accounts for about 55% of the planet's radius. On Mercury, the crust and mantle are just a thin shell wrapped around an oversized, dense interior. This discovery raised an obvious question. Why is Mercury's core so big? One theory suggests that Mercury was once much larger, with a thick, rocky mantle like Earth. But early in its life, it was struck by a massive object, a colossal collision that blasted away most of its outer layers, leaving only the dense metal core behind. This idea is supported by its size, density, and chemical makeup. But there's a problem. That kind of impact should have destroyed the entire planet or left it completely molten. And yet, Mercury survived. Another possibility. Mercury never had much of a mantle to begin with. Instead, it formed in a part of the early solar system where metallic elements were more abundant and silicates, the rocks that form Earth's crust, were scarce. In this version of events, Mercury is a primordial relic, a leftover from an early, chaotic phase of planet building where things didn't always come out balanced. Whichever theory is correct, one thing is clear. Mercury's interior is very different from its neighbours. Even more surprising is that Mercury's core isn't fully solid. Thanks to Messenger's measurements of gravity and rotation, scientists now believe the core has three distinct layers: a solid inner core, a liquid outer core, and a solid iron sulfide shell between the core and mantle. This means Mercury has a partially molten core, despite being so small and so old. And that brings us to one of Mercury's greatest surprises. Mercury is one of only 4 planets with a global magnetic field, the others being Earth, Jupiter, and Saturn. It's generated by the dynamo effect, the movement of molten conductive fluid inside the core. This motion creates electric currents which in turn produce a magnetic field. But Mercury's field is different from Earth's. It's much weaker, only about 1% as strong, and it's tilted and offset, especially toward the north. This asymmetry is still being studied. Despite its weakness, Mercury's magnetic field creates a magnetosphere that interacts with the solar wind. Messenger discovered that Mercury experiences magnetic reconnection events, where the planet's magnetic field lines snap and reconnect, releasing bursts of energy and accelerating particles toward the surface. These bursts are violent and brief, forming miniature auroras and magnetic tornadoes similar to those found on Earth, but happening far more quickly and without the buffer of an atmosphere. Another unexpected feature? Mercury has a tail, like a comet. It's invisible to the human eye but can be detected in ultraviolet light. This tail is made of sodium atoms, pushed away from the planet by solar radiation. It stretches for millions of kilometers behind Mercury as it orbits the Sun. The source of the sodium may be micrometeorite impacts or surface reactions caused by solar wind. So even without an atmosphere, Mercury is shedding material into space, forming a ghostly plume that trails the swiftest planet. Mercury is the least explored of the rocky planets, and it's not for lack of interest. It's incredibly hard to reach. Because it's so close to the Sun, spacecraft approaching Mercury must slow themselves down against the pull of the Sun's gravity, using clever orbital mechanics and gravity assists to enter orbit without burning excessive fuel. Only 3 spacecraft have ever visited Mercury, and only 2 have orbited it. In 1974, NASA's Mariner 10 became the first spacecraft to visit Mercury, and the first to use a gravity assist, swinging past Venus to reach its target. Mariner 10 flew by Mercury 3 times, capturing over 2,700 images and revealing a cratered surface that resembled the Moon. It discovered no real atmosphere, and to everyone's surprise, it detected a magnetic field. But Mariner 10 had a limitation. Due to Mercury's slow rotation, it only photographed one hemisphere. For over 30 years, the other side of Mercury remained unseen. In 2004, NASA launched MESSENGER, short for Mercury Surface, Space Environment, Geochemistry and Ranging. It took over 6 years of gravity assists from Earth, Venus and Mercury itself to finally enter orbit in 2011. MESSENGER became the first spacecraft to orbit Mercury, and it changed everything we thought we knew. Its key discoveries include 100% surface mapping of Mercury in high resolution, confirmation of water ice in polar craters, discovery of hollows and widespread volcanic plains, detailed study of the magnetic field and its anomalies, measurement of Mercury's core size, confirming it as the largest relative core of any planet. MESSENGER orbited Mercury over 4,000 times, collecting more than 10 terabytes of data. In 2015, after running out of fuel, it intentionally crashed into Mercury's surface, becoming a permanent part of the planet it revealed to us. Now, a new chapter in Mercury exploration is underway. In 2018, the European Space Agency and Japan's JAXA launched BepiColombo, a dual-orbiter mission with the most ambitious plan yet. Named after Italian scientist Giuseppe BepiColombo, who calculated Mariner 10's gravity assist trajectory, this mission aims to unlock Mercury's final secrets. BepiColombo consists of 2 orbiters. The Mercury Planetary Orbiter, ESA, designed to map the surface and study geology. The Mercury Magnetospheric Orbiter, JAXA, focused on magnetic fields and plasma interactions. Getting to Mercury is no simple feat. BepiColombo must perform 9 flybys, 1 of Earth, 2 of Venus, and 6 of Mercury before orbital capture in 2025. Once in orbit, it will spend at least 1 Earth year, possibly longer, investigating why Mercury's magnetic field is offset and asymmetric, how its surface evolved over time, whether it's still geologically active, how its exosphere and sodium tail change over time, and whether Mercury's unusual composition is a clue to how inner planets form. Visiting Mercury isn't just hard, it's expensive. Spacecraft need to slow down as they fall toward the Sun, which burns fuel. That's why gravity assists, using other planets' momentum, are essential for orbital insertion. And then there's the heat. Mercury receives 10 times more solar radiation than Earth. That means spacecraft need special shielding, radiators and materials that can withstand both extreme heat and deep cold, depending on orbital phase. BepiColombo's solar panels, for example, must rotate constantly to avoid overheat. Between Mariner 10, MESSENGER and BepiColombo, we've concentrated almost nothing about Mercury. Mapping its field, measuring its core, probing its magnetic field. Even after Mercury, and that's what Even after 2 full missions and a third en route, Mercury remains one of the least understood planets in the solar system. Each answer we uncover seems to open the door to 2 more mysteries. Let's explore some of the biggest. Why is Mercury's core so big? We know that Mercury's iron core is proportionally the largest of any planet. But why? Was it once a much bigger planet, stripped bare by a massive collision early in solar system history? Or did it form in a metal-rich region of the protoplanetary disk, close to the early Sun? Current models of planet formation struggle to explain Mercury's density, especially given its unexpected chemical makeup, which includes elements that should have vaporized at such high temperatures. Whatever happened, Mercury defied the odds and became a metallic survivor. Why does it still have a magnetic field? Mercury has no tectonic plates, no thick atmosphere, and a small size, all things that should mean it lost its magnetic field billions of years ago. Yet it still has one. Not only that, but it's strangely asymmetric, shifted toward the North Pole, weak and unstable. Is it maintained by convection currents in its liquid outer core? Is the solid sulfide shell around the core influencing the field? BepiColombo will attempt to answer these questions when it arrives, but for now, Mercury's magnetism remains a puzzle. What formed Mercury's hollows? Hollows, those bright, shallow depressions, are unlike anything seen on other worlds. They seem to form by the loss of volatile materials near the surface, materials that escape into space as gas under solar bombardment. But what exactly are those materials? How do hollows evolve? And why don't we see them on the Moon, which has a similar environment? These unusual features may help us understand volatile transport, space weathering, and surface chemistry in extreme conditions. Is Mercury still geologically active? We used to think Mercury was completely geologically dead, but some scarps appear geologically fresh, with no visible craters overlapping them, meaning they may have formed recently. Could Mercury still be shrinking? Are there Mercury quakes rumbling beneath the surface? Even without plate tectonics, planetary contraction might still be reshaping the landscape, slowly but surely. Could water have existed in the past? The discovery of frozen water in Mercury's polar craters was a shock. These areas are in permanent shadow and remain colder than -170 degrees Celsius. Cold enough to trap water ice for billions of years. But some scientists wonder, could Mercury have had more accessible water in the past? Was there ever transient ice migration? Could comets have delivered water that lingered temporarily in shaded regions? Though Mercury never had seas or rivers, its ability to retain water in isolated zones may be key to understanding how volatile elements behave across the solar system. How did Mercury form? This is perhaps the biggest question of all. Mercury doesn't fit the standard models. It's too dense, too metal-rich, and has too many volatiles for a planet that formed close to the Sun. Some propose that Mercury formed farther out, then migrated inward due to gravitational interactions. Others suggest it was the victim of violent early collisions, like Earth's moon-forming impact, but more extreme. There's even a chance Mercury is a failed core, a planetary embryo that never got the chance to grow. Understanding how Mercury formed will reshape how we understand every rocky world, including Earth. Interestingly, many of the rocky exoplanets we've discovered orbit very close to their stars, just like Mercury. They're often larger, hotter, and faster. But Mercury may be our closest analogue. By understanding Mercury's geology, core, and surface environment, we can apply those lessons to exoplanets orbiting distant suns. Mercury, in this way, becomes a prototype for the study of extreme terrestrial planets. Mercury is a planet of paradoxes. It's closest to the Sun, yet has ice. It's small and airless, yet has a magnetic field. It looks dead, but may still be changing. It was forgotten. But now, it's the focus of new missions, new models, and new questions. And that's what makes Mercury so important. It's not just a world of rock and iron, it's a cosmic fossil, a preserved relic from a time when planets were still forming. A tiny, ancient messenger carrying data from the dawn of the solar system. So why does Mercury matter? Why dedicate missions, research and resources to a small, airless rock that bakes in the sun's glare? The answer lies in what Mercury represents. Mercury is a survivor, a relic from the time of planetary formation. Unlike Earth, Venus or Mars, it never developed plate tectonics, oceans or a stable atmosphere. Unlike the gas giants, it never grew massive enough to hold onto a thick hydrogen shell. Mercury was forged early, battered hard, and locked in a slow spiral around the sun. And yet, despite that brutal origin story, it's still here, still orbiting, still changing. Studying Mercury gives us something that's becoming increasingly rare in planetary science: untouched data. The craters, cliffs, magnetic field and chemical traces on Mercury are windows into the ancient solar system before Earth even cooled. Every orbit, every scar, every crustal wrinkle on Mercury is a page in a 4.5 billion-year-old book. When we think about the planets, Mercury often gets ignored. It doesn't have the storms of Jupiter, the rings of Saturn or the drama of Mars. But in many ways, it's the most primal of them all. Mercury isn't a showstopper. It's a blueprint, a fundamental model of what rocky planets are built from, and that makes it essential. As we search for Earth-like planets beyond our solar system, as we analyze the atmospheres of super-Earths and hot terrestrials orbiting distant stars, we realize that Mercury might be the closest thing we have to those extreme exoplanets right here in our backyard. Its scorching dayside, freezing nightside, bare rock and magnetic field offer a real-world lab for planetary science. In the vast canvas of the cosmos, Mercury is a single dot, but it's a dot worth understanding, because from it we learn more about all planets, including our own. Let's go back to the beginning, to mythology. Mercury was the messenger of the gods, the one who could travel between worlds, fast, elusive and full of secrets. It's a fitting name for a planet that moves quickly, orbits close and has been so hard to catch. But like its namesake, Mercury carries messages, not divine ones, but scientific. Messages from the early solar system, messages about formation, survival and time. And now, with modern science, we're finally starting to read them. Thanks for joining us on this journey to the innermost world. We hope you've seen Mercury not just as a rock, but as a living time capsule, full of heat, history and hidden potential. This is Skyward Space Quest. Subscribe for more faceless deep dives into planets, space missions and cosmic wonders, one world at a time.